Let me briefly introduce today's colloquium and the speaker. There has been a change. You may have noticed that last time I announced a chemistry colloquium that has been postponed, and we took advantage of our colleague Paolo Natoli, who came from not so far away and could anticipate, because we originally meant to invite him for after Christmas. And today I'm replacing Andrea Ferrara, because Andrea Ferrara organized this colloquium, but he's away just because with this quick switch created some problems. So just a brief introduction. Today's event is devoted to cosmology, and in particular to a remarkable window in its far past that the universe grants us. This is the cosmic microwave background, or CMB, and from this colloquium you will learn some aspects of a beautiful enterprise that combines striking theoretical ideas, sophisticated experimental techniques, technology of high level, and also large-scale international cooperations, which is now a general trend in fundamental physics. Today's speaker, as I partly anticipated, is Professor Paolo Natoli of the University of Ferrara. Professor Natoli studied at the University of Rome Tor Vergata, where he obtained his laureate degree in 2000, and then his PhD with a colleague of mine, Nicola Vittorio, there. After a postdoctoral experience at the University of California at Santa Barbara, Professor Natoli became a postdoctoral fellow and then a junior faculty member at Tor Vergata. Then he moved to the University of Ferrara a few years ago, where originally he's a junior faculty member, and he's now an associate professor there. He held during the years a number of visiting positions at Santa Barbara, JPL Caltech, and Copenhagen, and received the Planck LFI Research Award. He played an important role in the Planck collaboration, and not only, also in previous collaborations, which are Herschel and Boomerang, and he's now involved as a team member in an important planned Japanese experiment. I think in the second part of the talk he will tell you about the evolving state of these high-scale cosmological experiments. Thank you very much.
Thank you, Augusto, for the nice introduction, and thanks to the Scuola Normale Superiore for inviting me. I think we can switch to the presentation, thanks. So we speak about the cosmic microwave background, which sometimes is called quite inappropriately, I would say, the light from the Big Bang. It's light that permeates the universe. And in this colloquium, I will focus on the use of this radiation to learn more about cosmology. I'll try to show you that it is a powerful cosmological tool. And this has been quite evident in recent years with the results from the Planck satellite, which I will largely focus on. So this is a standard picture of the evolution of the universe. I'm quite sure that most of you are familiar with this. So we now know that the universe is about 13.8 billion years old. We are obviously at the right side of this plot, and all this span is almost 14 billion years old. And we'll try to focus here on the early phase of the universe. So what is on the left-hand side? And you see a period of very abrupt, accelerated expansion, which is called the inflation, where really the initial condition of our universe are set. And then there is the expansion continues up to today, and we even know that nowadays it is accelerating again. You probably heard that. So the initial phase of the universe was hot. We speak of a hot Big Bang theory, and this means that ordinary matter as we know it is in the state of plasma. So that's the phase, the cloudy phase that I represent here. And at some point, the clouds dissipate, and this light, the microwave background, is emitted, and time is now about 380,000 years after the Big Bang. And this light is able to travel almost unaffected, a very long journey, until we detect it. So the universe expands. I'm sure you heard that one of the consequences of expansion is the cosmological redshift. So light from faraway objects, for instance, galaxies, get redshifted. And the reason for that is quite simple, because the wavelength of the photon, a photon that travels cosmological distance, you have a wavelength associated to light, and as every length in an expanding universe, the length of the photon increases, so the photon shift is to lower energy, and so you will see a reddening of light, which we call the cosmological redshift. So the microwave background permeates the universe. We know since the early 90s that this light has a black body spectrum. This was measured very well. So you can see the black body here. And the error bars on this measurement are so tiny that you cannot even see them quite well. And we know this because of a NASA satellite, which was flown between the end of the 80s and the early 90s, named COBE, which measured this spectrum quite well. And in order to see how accurate it is, you really have to take out residuals out of a mean. So we know that this is very close, very close to an equilibrium distribution, a black body, and we know the temperature of this black body quite well, and it's about 2.7 degrees Kelvin. Not only, so here you can see the effect of cosmological redshift on this black body, because its photon also gets redshifted until they travel this very long journey to us, and this shifts the peak of the distribution from very high temperature up to today. So when we say that the universe is a very cold place, what we really mean is that the temperature, the average temperature of the radiation that fills it is quite close to absolute zero. Okay, but it was much hotter in the past. And this is the reason why we think that the universe underwent this hot Big Bang phase. So the earlier you go backwards in time in the universe, the hotter it was. So going towards the initial singularity, you can exploit very high energies and use it as a probe for fundamental physics. Not only it's interesting to discuss about the spectral behavior of the cosmic microwave background, but the thing I will focus on this talk are its anisotropies. So you can think of the black body as the average of this radiation. Okay, if your eyes were sensitive to microwaves, you wouldn't see the background of the sky as dark, but you would see it filled with radiation of a given temperature. Then the thing you can ask yourself is what happens if I remove the average value of this radiation. And what remains are tiny anisotropies, that is variation across direction of the mean temperature of this black body, which are very small. So we say that the cosmic microwave background is anisotropic in about 1 part in 100,000. So these are variation of order 100 microkelvin over a background which is 3 Kelvin. So you can imagine that they are quite hard to measure. And these anisotropies are very important. You can think of them as a picture of the very early universe. Again, this light was emitted when the universe was 300,000 years old. And so you see in it the imprint of the inhomogeneities, the density perturbations in the early universe that over a long course of time, in billions of years, they have evolved in the large-scale structure of the universe, the clusters of galaxies and eventually the galaxies and the matter inside the galaxies that we see today. So this is really a link to the initial condition of the cosmological perturbations that have seeded the large-scale structure of the universe, and this is why we want to study them, to get a link to the initial conditions that we believe were set during inflation. So this was studied extensively by COBE, by another satellite, which was again a NASA satellite, which was called WMAP, flown in the early 2000s, and then again by the Planck satellite, and now we switch to Europe, since Planck is a European mission, so third generation satellite devoted to the cosmic microwave background, but launched and operated by ESA. So this was built to give the ultimate characterization of the temperature anisotropies, that is to exploit all the information that it's encoded in these fluctuations of the mean of the black body distributions that we see in this plot as spots. So Planck was launched in 2009 and was operated until 2012, and then we analyzed the data basically, and the last release happened last summer. So basically we are at the end of the life of Planck. Planck, you can consider it as a retired mission, and so we can now see what it really has produced. So Planck was operated around the L2 Lagrangian point, 1.5 million kilometers in the anti-sign directions, looking at outer space. It had at least a Joule libration orbit about this Lagrangian point. And the reason you want to operate a satellite there is that you really want to look at the cosmological background and have the Earth, the Moon, and the Sun at your shoulders. Those are powerful microwave emitters that will that would disturb the measurement. So you go to space in order to have a stable environment which allows you to integrate for a long time, and this is what Planck has done. So we are now at the end of this journey. We had other releases of data. The last release we call the legacy release, and this is what is left really for the community. So Planck, well, the primary product of Planck are sky maps. Planck is a microwave telescope. So it observed the sky from 30 gigahertz almost up to 1 terahertz. And you can see here that almost in every image, you can certainly see the anisotropies of the microwave background, but you can also see the bright emission along a plane, and that is obviously the plane of the galaxy, right? Since our galaxy is a powerful microwave emitter, okay, and you can see that it emits at the low end of the spectrum, since by plan, around 30 gigahertz, and this is mostly synchrotron emission by electrons which are spiraling in the galactic magnetic fields, and then this emission goes down until it reaches a minimum at about 70 to 100 gigahertz, which are two very good channels for cosmological observations of the background, so an open window to the universe. And then at higher frequency, you can see that the emission from the galaxy ramps up again, and this is basically cosmic dust. It's gray body emission from the dust which is hosted in our galaxy. So if you want to do the ultimate measurement of the CMB, you have to peel off the layers of unwanted local emission, diffuse emission from the galaxy, which might be very interesting from an astrophysical point of view, and it is indeed studied by astrophysical guys, but it's a nuisance from the point of view of a cosmology. So you have to peel it off. And you can see here on the right-hand side of the plot, I go back to the right-hand side later. So on the left-hand side, you can see the reason why you can actually peel it off. Because you have here, you have here on the left-hand side the CMB black body, and then you have emission from, radio emission from the galaxy, which is going down, and thermal dust, which is ramping up. So you can exploit the different spectral behavior of this emission to do what we call component separation, clean the CMB from the unwanted foreground emission. And this is a very important step in the pipeline of cosmological observations. So if you do this, you can obtain an image like that, which show the microwave background anisotropies, which are usable really almost over the sky. The percentage of sky that we are able to use is of the order of 90%. Okay, and then this can be exploited, basically, to do cosmology. There is another important piece of information, which is the fact that the cosmic microwave background is polarized, and to be accurate, is linearly polarized. So we know what linear polarization is a property of light, which you can measure by polarizers. Commonly used polarizer glasses do actually this to remove unwanted shiny features. And Planck hosted a version, to say it loosely, of these polarizers on board, so was actually able to measure the polarization of the microwave background. Although it wasn't really built for that, it is an extra feature that we were able to measure. So the CMB is expected to be polarized because the Thomson cross-section is sensitive to the polarization of the ingoing and outgoing photons. So if you have a situation here, let me show this, let me try to show this again. If you have a situation where you have an isotropic sky, and you see light scattering off an electron which is coming from two directions 90 degrees apart to flag a quadruple distribution. If the background is isotropic, you would not expect to have any degree of polarization in the outgoing state. But if the background is anisotropic, as it is the case, then the two vertical polarization will be different, and you actually expect to have a polarization in the final state. So this is something that can be exploited to have extra cosmological information, and this is what Planck has done. So now you have an image of the frequencies observed by Planck in linear polarization. So you have two quantities that describe linear polarization, which are the Q and U Stokes parameters, and also the polarization total intensity on the right column. So this was really an improvement of Planck in the latest release. One thing that appears very clear in this image, even if you have not seen them before, is the fact that the galaxy is quite intense. And this is indeed the case. Yes?
Can you read the scale down? I mean, the colors, can you tell us?
Yeah, so these are basically, it's a composite scale to catch different frequencies. So the lower the lower images are microkelvin CMB of black body temperature, lower frequencies. And
the difference in frequency.
Yes.
The color is different in frequency.
No. The color is different in intensity. This is microkelvin CMB, so you measure the polarization in the same units that you use to measure temperature. Okay, and the funny thing is that the scale. No, red means hotter, basically, hotter. And
how do I read the polarization there?
You read the polarization because these are Stokes parameter for linear polarization. So the Q and U are the usual Stokes parameter for linear polarization, and what you plot here is the square root of Q square plus U square. If you want to have the degree of polarization, which is what you probably have in mind, you have to divide this by the intensity. And so if you are speaking of DCMB, the degree of polarization of it is expected to be much lower than 10%.
But
okay.
The square root of U square plus
is microkelvin as a map. So what you see here.
No, that I know, but I want to see how I understand those colors. And I haven't.
Yeah. Well, those are simply, it's a temperature fluctuation in microkelvin, the same exactly the same unit that you use for temperature.
Yes, but,
okay.
But it is related to...
It's related to the linear polarization Stokes parameters, which are these two columns here, so Q and U. And what you see here is simply the square root of Q square plus U square.
Where there is maximum polarization in that plot, for example, such a way that I understand.
But in order to see where the polarization is maximum, you have to divide by total intensity, which is not done on this plot. These are physical universe, are microkelvin CMB. So you are only sensitive in this plot to the polarized part. You are taking intensity out. If you want the degree of polarization, you can divide by total intensity. Okay, so, but this is galaxy. This is mostly emission from galaxy. You are not able to see the microwave background polarization here, since it's very weak. It's of the order of microkelvin. Okay, and so here you would see polarization of the galaxy, which for dust is a fraction of 10% or so at maximum. Okay, right. So you have to unveil the sky also in polarization again, and here it's much more difficult because there is no window, as you can see. So DCMB is well below the foreground at most angular scale. So this is a difficult job, which has been done nonetheless. And you can see here an image of the polarization of DCMB, which is represented here as this vertical bar, over-impressed on a smoothed image of the temperature anisotropies. And if you blow up here, so going basically from this here to this, you can see how these vertical bars, again, this is a blow-up of the image, are correlated. And in fact, since the source, the longer the bars, the higher the polarization. Okay, keep in mind that there is noise in this measurement, but you can see a certain trend of correlation between the temperature plots, which are in color, and the polarization. Okay, and this is something that you would expect because the source of this polarization that you are measuring it's again the density perturbations. Okay, so if you stack, for instance, on the extrema of the temperature field, you stack all the extrema and you average the polarization, you would expect to see something like this. Okay, this is a hot spot of the microwave background, stacking of hot spots, and you see how the polarization nicely correlates with it. Actually, the correlation that we measure from Planck data is indistinguishable from a simulation. Okay, so polarization, you can think of it as an extra field which carries extra information and you can measure. Okay. So how do you measure this information? How do you go from these spots or these lines to cosmology? Well, this is a random field. We know that random fields are studied via correlation functions. The CMB is expected to be mostly Gaussian, so the correlation function, which is really most important, is the two-point correlation function, and you basically want to measure here what degree of anisotropy you have at a given angle. So how these spots are correlated across temperature, and temperature to polarization, and polarization to polarization. For polarization, there is an extra degree of freedom, since polarization is a tensor field, okay, and tensor field and spin 2 field, and the spin 2 field you can decompose in different modes that have opposite behavior under parity. You can call them the E mode and B modes by analogy with what you can do with the Maxwell tensor, the electromagnetic tensor. Okay, so it happens that the density perturbations, which are parity invariant, can only excite the E modes of the cosmic microwave background. Okay, so all the polarization we are able to see in the previous plots is actually sourced by density perturbation, and we know that it's an E mode it's sourced, it's E mode, basically. We also expect, if there was a certain degree of tensor perturbation in the initial conditions, that this polarization also exhibit B modes. Okay, if you are able to see a B mode in the microwave background and you convince yourself that it's primordial, you have seen a perturbation which is not a scalar, but it's tensors. Those are believed to exist. I will go back to them at the end of this plot when we talk about the future, but they are far beyond the sensitivity of Planck. Okay, so what we have here is that you want to do analysis on the sphere in terms of correlation functions, and in order to do that, it's natural to go in Fourier space. So to speak of the transform of the correlation function, which is a power spectrum. So a power spectrum, an angular power spectrum in this case, it's an object that measures the degree of anisotropy you have at a given scale. So if you have a look at this, you will see this power spectrum, this curve, and also on the top of the plot, you see a decreasing angular scale. Okay, so this tells you how much anisotropy I have at a given scale. If you want, you can relate this to the spherical harmonic multiple L, which would be increasing. So you can see that this plot is quite rich and exhibits peaks. And these peaks you can relate to the oscillation in the original plasma. Okay, since there was a competing mechanism between gravity, which tend to make perturbation collapse, and radiation pressure, which made them expand. So you're really looking at the conditions in the primal plasma here. Okay, and the thing is that this spectrum is sensitive to the cosmological parameters that describe the content of the universe, okay? So by measuring this, you have a window on the measurement of cosmological parameters. So the job is that you take a map, you transform it to get a power spectrum, and then from the features of the power spectrum, you can measure the cosmological parameters, literally weight the universe or get its chemical composition and the features of the initial conditions of these perturbations. So this is the power spectrum that has been measured by Planck. It's the latest release. There is no fit here. These are just the data that we see from the sky by extracting the power spectrum of the maps. Okay, so you see that these peaks are a reality. They are well measured. There are about 7 peaks in this image. And you can also see a region here on the left-hand side, which again corresponds to the largest angular scales, where the errors are large for a fundamental reason, because we have only one image of the universe. This is called cosmic variance. And then you can try to make a fit and to see whether this is really agreeing on the cosmological models. So we are able to predict the anisotropy spectra based on cosmological parameter. And so the question is now which cosmological parameters are best for a certain class or model are best fitting this spectrum. And so this is the fit, astonishingly based only on 6 parameters, which I will describe on next slide. And you can see that the fit is quite good. So 6 cosmological parameters actually are able to explain quite well, almost always, almost everywhere, the features that we see in the microwave background. And you see that the residuals are quite under control. There is only this doesn't work anymore, but I'll do with my hand. There is a region here which is something off scale, which is a little bit low, and we'll get back to this.
CVL stands for what?
Cosmic variance limited. So cosmic variance, so this is a measurement where the error budget is entirely given by the fact that you have only one picture of the universe. You cannot travel to a galaxy far, far away and observe another image of the microwave background. The error bar on the residual is an estimated error, which is largely based on cosmic variance here. It's almost entirely based on cosmic variance, unless perhaps here in this region where you see effects due to noise. Okay, so the error bars you see here is given by cosmic variance, basically, on this temperature spectrum. You can also look at polarization spectra. This is an E-mode polarization spectra, and this is a temperature to E-mode correlation polarization spectra. The nice thing here is that we did not attempt, for this case, to fit those spectra. There is no extra statistical leverage here. What we are doing here is simply make a prediction to polarization given the temperature spectra that we have measured, so the fit that you have seen in the previous plot, and this generates a set of curve, and now we see how this set of curve actually agree with the data for polarization to polarization correlation and temperature to polarization correlation. So this, on the right-hand side, would be the harmonic version of the stacking that we have seen in the previous plots. And I would say that this is quite good. Then of course, yes.
When you stop the plot of the error at 30, is that, do I understand well? I mean,
no, it is
green line.
The blue line here. This is what you mean. So why there is a 30 here?
No. Why you stop the drawing of the yellow line, is it yellow, orange line at 30?
You mean here at 30 here? Well, this is simply because there are different units on the right-hand side and left-hand side. So, and the split down is a multiple of 30.
Right.
Okay.
That doesn't explain yet why you don't have the orange line.
Well, you don't have. No. The orange line is basically given by the dispersion here, okay, of the original data. Because we did not plot it. Okay, that was a choice. It is large because the errors are larger again due to cosmic variance. So it's a totally different regime. Okay. So it's simply a visualization choice. We're not expecting to draw information on this, except that the prediction from temperature does fit polarization very well. So we are understanding the machinery. Okay, another thing I wanted to talk about, perhaps quickly, is the fact that there is another spectrum that you can measure from the CMB, which is connected to the fact that the CMB is weak-lensed while it travels towards us by the fact that it travels to structure formation. It travels to dark matter potential. So this induces weak lensing, which deflects the microwave background. So you have a deflection field, basically. Okay, you can measure this deflection of light, which is quite small, and this has an immediate consequence that it will smear a bit the angular power spectrum. Okay, so the fact, yes.
Imagine how you can do that. Is it by simply, superimposing the observation to the field?
Hold on a second. I think it will be clear in an instant. So the effect, the theoretical effect, you can predict between lensed and unlensed, and this is what you actually can see here. So one consequence is that it will smear the angular spectrum. Okay, but there is also another important consequence which will create non-Gaussianities on the map. It will induce a non-zero 4-point correlation function. Okay, and this you can measure. So you can put in the theoretical machinery that you analyze the spectrum with the fact that you would expect this mirroring and fit for it, and this is what you do. But you could also measure the 4-point correlation function on the map. Okay, and you can get this, you can imagine this as an angle-angle spectrum. So each angle couples two temperatures. So this is temperature, 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 temperature. It's a 4-point function. And this spectrum you can actually measure from the map. And based on this measurement, you can...
You have to know that it's not basic, right?
You have to know that it's not degenerate with the other effect. Right. This is probably what you meant. And it turns out that it's not degenerate. Here in the power spectrum, you can expect some degrees of degeneracies because there are other variations of cosmological parameters that can mimic a similar effect. But here, this is a 4-point function, which is not what you're expected to measure with a 2-point function. So this is quite clean. Okay, then
if the density distribution is Gaussian or not?
Yes, but we know that it's very Gaussian. Okay, we know that the CMB is very Gaussian. This is actually another measurements that we can make. We know that the initial conditions are Gaussian. This is a prediction from inflation. So let's move forward. There's another effect in lensing, which is the fact that if you have a pure E mode in polarization, the lensing will distort it a bit, okay? So it will make it no longer parity even. So it will make a B mode appear out of E mode. This is not a primordial B mode. It's simply a distortion that you can use to leverage out extra cosmology from it. This is actually measured, while the primordial B modes are not. So this is a representation and snapshot of our current understanding of the CMB spectra by Planck and other experiment. You see that temperature is measured extraordinarily well. Polarization is measured quite well, especially at the intermediate scales. And then you have B modes from lensing, which is what I was talking about, which are also measured but not well. This is TE, which is measured very well, and this is 4-point correlation function lensing. So what is missing in this plot are the B modes, of course. We'll get back to that later. For now, let's talk about the 6 cosmological parameters that we actually measure from Planck, and they are the baryon density of the universe, the dark matter density, the CMB acoustic scale, the optical depth to a scattering surface, and the amplitude and tilt of the initial conditions. Okay, the spectrum of the initial perturbations. So there are also other derived parameters. One of these is the Hubble parameters, which is quite important in cosmology and a source of recent discussion. I will briefly discuss this. So all these parameters, most of these parameters are measured with sub-percent precision or even better. So the relative error is very small in almost all of them. So Planck, when was designed, promised precision cosmology, and we are really at it, at least in this very basic 6-parameter, which is called the Lambda Cold Dark Matter model. So you can see that the level of precision that Planck has reached over time, Planck and experiments pre-Planck have reached over time, and we are really pinning down the cosmological parameters out from the pre-WMAP, which really means pre-2000, so not a long time ago era. Now we are really pinning down our knowledge of these cosmological parameters. So everything right? Well, sort of. So this is probably the most technical plot that I will try to describe here, and this has to do with tensions. So we discussed here the Planck results. So one fundamental question that you would like to ask is, how are Planck results related to the other cosmological results, other cosmological data sets? So there is an experiment called DES, the Dark Energy Survey, which really counts faraway galaxy, measures the cosmic shear from this galaxy, measures faraway supernovae. You can do cosmology with this. Okay, so basically on this plot you have, on the left-hand side, you have omega matter, the matter content of the universe, versus sigma 8, which is a parameter that is related to clustering. So Planck is the tiny spot here at the center, okay, and you can see that there is perhaps a mild tension with the same parameter measured by the DES, where the errors are larger. Not a very significant tension, in the order of 1 to 2 sigma. But there is some tension in the fact that DES wants to measure a slightly lower sigma 8 and a slightly lower omega matter. Where there is a very significant tension is with the measure of H naught. H naught is the parameter that describes the expansion of the universe. Okay, the present value of the Hubble constant. This can be measured by Planck, and is measured by Planck, and you see the likelihoods here on an H naught omega matter plane. So Planck will basically be here. But you can also measure this parameter directly by looking at Cepheid star in faraway galaxies. That was the Hubble key project. And you can see that there is a significant degree of tension. So this would be called the distance ladder measurements, because you calibrate distance by using a ladder which relies on distance indicator, and this is done by the Hubble Space Telescope and other observations just by directly looking at the expansion of the universe. There is no model assumption in it. Okay, this gives error on H naught, which are larger than what you can derive with DCMB.
DES is based on lensing or what? DES is based on what?
DES is based on lensing. So you see here, when it measures sigma 8 versus omega m, you basically have DES lensing. Okay, but also DES measures the faraway supernovae. Okay,
so isn't that? I try to understand the difference between the RIS and DES.
No. So this is a different plot, right? So here we are discussing RIS here, not there.
There is DES as well there.
Yes.
What's the difference between DES and RIS there? Yes, I was coming to this. The point is that with
experiments like this, which really counts the galaxy, you can attempt what is called the inverse ladder measurement. So instead of making a measure of the expansion from the low redshift universe here, you can try to measure the expansion based on galaxy at high redshift. In order to do that, you have to assume an inverse ladder. So you have to assume that you can calibrate what we call the sound horizon, okay? This is normally done with the CMB, okay? So there is, in this inverse ladder measurement, there is a, if you want, a prior which comes from the microwave background, which is the sound horizon, okay? But that this is what is done here, for instance. That you can calibrate on Planck or on other CMB experiments, okay? And if you do that, you would get from the inverse distant ladder a value of H naught, which is very compatible to what Planck gives. And in tension, in quite strong tension, now the tension is about 4 sigma, to what comes out from the direct measurements, okay? So this is something given in this plot. You can see how the Planck measurements are really getting some tension with the direct measurement. And this is, so to speak, an unsolved issue, okay? One way of solving it in the near future will be to rely on the so-called cosmic sirens. Okay, so here you have the direct measurement versus the Planck measurement, which are these bands. And this is the H naught measurement, which came from the only neutron star merger which has been observed so far. This is another very direct measurement of the Hubble constant, because it simply calibrates the luminosity distance versus redshift. Okay, relationship. For some reason this happens, the peak of this distribution happens to fall in between the two. We'll see what happens. They claim that with 50 objects they will be able, 50. They will be able to claim to sort out the difference. Okay, now how much time I have left, Augusto? I think 10 minutes. Okay, let's try to say something about the extended models. Okay, so here there are several ways you can extend the basic lambda CDM models. The one I would like to concentrate about is assuming tensor perturbations, which I've already measured, so assuming some tensor to scalar factor, okay? Then you could also play with primordial non-Gaussianity, as you were mentioning earlier. I'm not going to discuss this. I would like to spend a few words about the properties of neutrino, which is another thing that we can measure with Planck. So again, if you assume that there are that inflation has excited also tensor perturbations, you can try to measure them, their effect. And this is something that Planck has attempted to do. So if you see this plot, this is a likelihood plot for the tilt of the primordial perturbation, what is called the primordial spectral index of perturbation. And one thing that you can see that Planck does well is to pin it down at a value which is almost 1, but not exactly 1. And this is one of the key predictions from inflation, because inflation has to end, okay? And one of the effects of this is that the spectrum of primordial perturbation is not completely scale invariant, as we say, almost scale invariant or nearly scale invariant, which means that it has to be less than 1, and this is what we measure. Then on the vertical axis, we have the tensor to scalar ratio, the amount of tensor perturbations, which are not measured, so you only have an upper limit there, okay? And you can see that this plot is really what is needed, is one of the plots that is needed to to actually constrain inflationary models. We are not at the level that we can constrain things down here, but we can already start excluding particular models of inflation. So the exploitation of the CMB is moving from the regime where you can actually probe different models of inflation, which exits from the state of being a paradigm, but you can actually probe physical theories. Okay? So one key prediction of the inflation was to have a spatially flat universe with a nearly scale invariant spectrum of density perturbation, and that's the measurement of the primordial spectral index, which is less than 1 at around 6 to 8 sigma, now with Planck, depending on the choices you make. And this is expected, the primordial spectrum is expected to be almost a power law, which is what we measure, dominated by scalar perturbation. We have these upper limits on the tensors, which would be nice to see, but we haven't seen that. Gaussian, adiabatic, and there is no contribution from topological defects. This is sort of an inflation checklist given the results of Planck. So most of the prediction of the inflation we have actually seen, except for the tensor.
Advocate,
yes.
would say that the truly only, quantitative prediction that you get is the first, right?
Flatness.
All the others are not quantitative predictions. They are, at the moment, qualitative predictions.
Would you allow me?
Which are in the right direction, as you say, but
would you allow me to disagree, at least on the spectral index, which inflation predicts to be less than 1, and this is what we quantitatively measure very, very well.
I know that, I call a quantitative prediction when you compare two numbers, right? One experimental and one theoretical. Now, less than 1 is an indication that you are in the right, but it's not what I would call a quantitative prediction.
In this sense, I would totally agree with you that we are not at the level where we can exploit the information on the spectral index to measure inflationary models. Although I would also advocate that, sorry, I need to go back, that we are starting to do so, right? Because some of these models are clearly getting outside of the NSR plane.
But the zoology of models is always
yes, absolutely so. Absolutely so. So you would need an experiment which goes down here, okay? And this is food for the future. It's not Planck, absolutely. Yes, okay. So improvement in inflationary parameters. Yeah, I'm running, unfortunately, out of time. Let me discuss two things very quickly. One is the handle that Planck has on neutrino masses. These are now the tightest constraint from a single experiment. So here, the parameter that you measure is the sum of neutrino of the masses of the neutrinos. And again, I want to show this to highlight the tensions in a plot which is versus H naught. Okay, so there is a tendency to resolve this tension by changing the model, which allows from non-zero neutrino masses. Okay, fine. But if you do so, you will tend to go in this region, and if you look at the color code, this will give you lower sigma 8, okay? So it goes in the wrong direction for sigma 8. Also, well, this, I can briefly, this is the number of neutrino family, which is predicted to be 3, around 3, if you neglect the coupling effects. And again, so Planck does exclude a fourth fully thermalized neutrino with some significant 3.6 sigma. Again, you can try to reconcile the tension with H naught by allowing this likelihood plot to shift a bit, by allowing for an extra unseen component, like a stellar neutrino. But if you do so, then again you are losing an handle on sigma 8. So you are exacerbating the tension with matter clustering. Okay, so not easy to get out of the tensions by simply changing the basic parameters of this model. And then let me go back to another thing, which is anomalies in the cosmic microwave background. We noticed earlier that here, although the errors in these regions are dominated by cosmic variance, there is a clear tendency to go low. This is not very statistically significant, but it is something which is seen in the data. It's significant, it's order 3 sigma. Okay, and that one of the possibility is that we are actually seeing a feature of inflation which is not really scale invariant, but we see only in the large angle modes, which are the longest, okay, so the earliest from an inflationary point of view. This is a window on the beginning of inflation. So in the context of string theory, it can be natural to model this by giving up the idea of that inflation is driven by slow roll of the inflaton, but introduced a fast roll to slow roll transition. This would naturally give you a scale, which is this delta, which makes this power spectrum non-scale invariant anymore. And in this context, the lack of power that we have seen in DCMB spectra is actually due to this delta. Okay? This has been wrongly exploited, so Augusto here has been one of the pioneers of these ideas, and we have tried to measure this from Planck data. So one thing that becomes evident to us is that if you just decide to take less data from the sky, so you impose a larger mask on Planck data, you can see that by eye, the anisotropy get less intense, so there is less power. But this is not the only story, because there's another transformation that you can do on the map, which is to divide that between parity even and parity odd modes. So this is simply the temperature map. So the parity here would be given by the parity of the spherical harmonic. And you already see by eyes that these maps are very different. Okay, so one has less power and the other one has more power. So you can turn this into a measurement for this parameter delta for several galactic cuts and for the even and odd maps, and you can see something which is really funny and not understood at the moment. So the fact that the even map yields a very stable measurement of this new inflationary parameter delta, while the odd map does not. Okay, there's that exhibits a dependency on the galactic cut. Okay, so this is sort of ongoing work. So this fact that we have that the even multiples are consistently lower than lambda CDM expectation is something that we are really working on but not completely understood. So this can be pinpointed only by future experiment. You have to have a satellite which does for polarization what Planck has done for temperature. This is really something in the future. I think my time is over, but I wanted to give you a glimpse of what lies in the future of CMB observation, which is not only a matter of sensitivity, so you can build experiments that are much more sensitive by Planck just by exploiting the sheer numbers of detectors. Planck has 70 detectors on board. Now technology allows to go to 100,000 easily. Okay, so it's not a question of sensitivity. It's more a question of systematics. If you really want to exploit the B modes, this is quite a busy plot, you have to go here. So this is the unseen part of the spectrum. These are angular power spectra prediction for different value of the temperature to scalar ratio in the B modes. There is no measurement here, no data. But what we know is that this is completely dominated by galactic emission. So we have to be able to clean it well. In order to do that, there is a plethora of experiments ongoing on the ground, which is dominated again by US, while we, Europe, had the lead on satellite with Planck now, balloon-borne experiment, and satellites. Now, the situation for satellite, it's not extremely good, since basically we have only one contender left, which is this LightBird satellite that Augusto was mentioned. There is something going on balloon. In particular, there is something going on balloon, this is ground, in Italy, and Pisa is playing a major role on this, so I'm very happy to mention this. This is a large-scale polarization explorer, which is a balloon experiment for the high frequency and a ground-based experiment for the low frequency. So the low frequency is in Tenerife, but the high frequency flies on a balloon, and the technology for this is also built here in Pisa. Okay, and so you can put together the observation from Tenerife, and this LSP balloon flies around the Arctic Cap. This is expected to happen in a year from now. Of course, the future is more on the satellite side. Let me skip this. So LightBird is a satellite which is now in phase A, where several people, including the group in Pisa here, is participating. This is a mission which, again, will fly to L2 again. It has a scanning strategy which is more adapted to measure polarization. I skipped the larger, very large frequency range to do efficient component separation in polarization. And if we are able to do this, and this mission flies, we'll be able to measure very well the tensor to scalar ratio, which is with an error which is of the order of sigma of the tensor to scalar ratio has to be 10 to the minus 3, which means that if you have 1% of tensors, you'll be able to pinpoint very well and see the primordial gravitational waves. And seeing the primordial gravitational waves is indeed important because they will be a manifestation of the quantistic nature of gravity, a real window on the inflation. Okay, so you can measure not only the energy scale of the inflation, but do the counterpart of what we have done by looking at the classical gravitational wave from astrophysical objects. You can see gravitational wave from inflation, which are really excited from the quantum properties of gravity.
This LightBird is basically originated from Japan?
Well, it is a JAXA mission with a significant contribution from NASA. JAXA is the Japanese space agency. And now I would say a significant contribution from Europe, which is not clear whether will be supported by ESA, as was the case for Planck, or by the national agencies. So that is, I think,
for example, has not yet decided.
INFN is interested, I would say so. So the satellite up to now, it's not approved. It will go phase A down selection in a few months. I would say that there is a solid interest from INFN, and we are told that if the mission is selected, as we hope, INFN will be happy to participate. Selected by JAXA, yes. Down selected by JAXA. Okay.
Thanks, Paolo.
If there are more questions or comments, I will come and give you the microphone. Riccardo asked every question.
Can you please go to the slide where you showed like the 6 parameters of the lambda CDM and the determination?
I need the presentation back in order to do that. Okay, so you want, let me see. That's probably better if I try to do that like this. So it's quicker. No. Yes. Yeah, this is kind of, we are almost there, huh? So you mean this?
Exactly this, yeah.
I didn't
indeed,
discuss this in depth.
What I mean, my question is about what is the precise definition of dark matter density here as compared to total matter density? Because if it's defined as, total minus baryon, I don't understand why the relative error becomes 2%, 2.3%.
Total matter density is dark matter plus baryon.
And how do you get a relative error of 2.3% by adding two numbers, which is 1% and 7 per mil?
So why are you getting a larger error?
If I sum in quadrature.
That's an interesting question. It's
easier the separation than the top. Is that what
exactly.
Yeah,
I believe the other way around can happen, right? But the separation cannot be easier than the sum. The other can happen, the other way around.
So, yeah, no. So the issue is that this is a physical density, so
okay,
it's multiplied by h square. Yeah, obviously. And so the errors on the Hubble parameter jumps in. Yeah, that's the reason. Right.
Questions or comments?
So the error in that slide is on my side because what you measure as lambda CDM is the physical density, which is multiplied by h squared. By that is simply the fraction of the critical density, which is in matter. So there's the Hubble constant on that. Right.
I have a non-technical question. So just a curiosity, what will happen to the satellite now that the mission is over? To the physical satellite?
It's already been deorbited from L2 in 2012, so the last year of operation. So ESA doesn't want its satellites at the end of the life to stay around in L2 because it's a sweet spot for astronomical observation. So they will use the remaining hydrogen on board they fire the rockets basically, and they take it out and they put in a sun orbit. And as it happens, flight dynamics can be understood up to a certain point. So they cannot guarantee that in 100 years or so it doesn't come back to L2 to give some issues to the satellites which are there. Okay, it's completely dead. So actually, when they turned it off, they sent a special command which killed the satellite so that it cannot turn on again, for instance, because of a cosmic ray hitting the electronics. Okay, so a lot of money which is lost in some sense.
More questions or comments? So if not, we thank Paolo again, and there are some refreshments at the end of...
Grazie, veramente ho apprezzato le sue domande.
Grazie, senti un po', ma scusa, un'altra.
Sì.
Allora, è corretto dire che per BAO siete pure voi i principali formatori o no?
No, nel senso noi possiamo usare BAO sono galassie, vedono una cosa simile, cioè quello che noi vediamo nel plasma primordiale, cioè l'orizzonte del suono del CMB, le oscillazioni acustiche. Sì. La CMB funziona calibrando la relazione di distanza-angolo, perché tu vedi